So in the last stereoisomerism class, I had told you that there are still few cyclic structures are left where we have to understand the geometrical isomerism, and there are some cases left where carbon double bond nitrogen and nitrogen double bond nitrogen bonds geometrical isomerism is yet to be done. So today we'll finish off our last cyclic structure for geometrical isomerism, and then we'll start with carbon double bond nitrogen and nitrogen double bond nitrogen. So let's talk about the last case, that is diphenyl. So diphenyl is nothing else but two phenyl groups attached to each other. We also call them biphenyls. This is how it is. So basically your benzene ring itself is planar, but two benzene rings, if you consider, two benzene rings are attached with a single bond, and single bond can rotate freely. So now what happens at instant of time, these two rings can be in the same plane and can be in the different plane. So how is it? Assume these are the two rings, one brown and one this one, and these are attached through a single bond. So there is a single bond in between. Okay, now when the single bond will rotate, there is a possibility that chain can also rotate. Not possibility, basically chain will rotate. Okay, so the carbon which is attached will remain as it is, but rest of the ring will rotate. Bond rotation means what? That your ring will go in a different plane. So this is when both are in the same plane, and this is when they're in the different plane, right? So one is parallel to the board, another is perpendicular to the board. This one which is on the left is parallel to the board, one which is on the right is perpendicular to the board. So now just assume the same thing happening over here. So one, I have so this is my one ring, this is my another benzene ring. So assume this is parallel to the board, and this is going to rotate. Right now it is parallel, it can go and switch to the perpendicular to the board also. Okay, parallel to the board. Right now both are in the parallel plane. So many a times this question also has been asked in the competitive exams, that when biphenyl is there, how many carbons do you think can be in the same plane at an instant? Minimum. So basically the one benzene ring has 6 carbons, and all those 6 carbons are anyways going to remain in the same plane. In the cyclic benzene ring, all the carbons are in the same plane. Now when you rotate it through this bond, the other ring, this carbon and this carbon will still always remain in the same plane, whereas other carbons can either parallel to the board or can be perpendicular to the board. I had shown you this way. Just see this again. I have, let's say, hold this, and it is attached to the carbon. Assume here is a carbon, this is a carbon, and this is the carbon. So even when I'll rotate carbon's plane, this carbon where it is attached with the bond, it is not, the plane is not changing. The plane for other carbons is changing. In fact, this carbon also, its plane is not changing. Okay, so plane of these two carbons will not change, whereas rest of the other carbons plane will change. So at an instant, minimum 8 carbons can always be in the same plane when you talk about the biphenyl. Okay, this is a commonly asked question. Now how we are going to understand the geometrical isomerism in biphenyls? We are basically going to take a specific case of ortho dash tetra substituted diphenyl. Now what is ortho dash tetra substituted biphenyl? This is this. So basically any attachment which will be present over here, these are the ortho positions. Ortho position is which position? First position. So here is one group, and with respect to it, the first position is this and another first position is this. So these two positions are ortho, and these two positions are also ortho. But because we are talking about two different benzene chains, we have just named them ortho for one benzene and ortho dash for the another benzene. Okay, here we are going to understand the geometrical isomerism. Okay, now let's take the first example. This is our first example, in which I have attached NO2 on one carbon and COH on the another carbon. So basically on one ortho position you have an NO2, on another ortho position you have COH. Again you have, now here you have to carefully look, this ring is parallel to the board and I have drawn it elongated. Okay, so it's one ring is like this and another ring is like this. Okay, this is perpendicular to the board, so planes are different, right? Only this carbon's plane and this carbon plane is going to be same, rest of the carbon's plane is different. So COOH here and NO2 here, both are in the different plane as compared to NO2 and COH over here. Now, all the previous cases what we have learned for spiranes, cumulines, cycloalkalidenes, there we have seen that if the groups are in the different plane, then their L1 and L2, basically distance with respect to each other, doesn't change. If they're in the different plane, the group's distance doesn't change. We have already discussed this in spiranes, cycloalkalidenes, cumulines. If you don't remember this, go back to the same videos, watch it again, and you will relate it. Okay, so because these two are in the different planes, the difference between these groups are not going to change no matter NO2 is here or NO2 is here or COH here or COH is here. It can be, if it would be together, it would have been called cis, or it is opposite to each other, it will be called trans, but this will not call cis and trans because the distance is not changing. They are just in different planes. Their distance is same. NO2's difference with distance with CO2 is same as NO2's distance with another NO2. So it's not going to change. So no GI will be shown because these are non-planar. Whereas if I take the case like this, where my first chain is perpendicular, is parallel to the board. Now here I have attached 3 cyclic rings, 3 benzene chains basically. Another is perpendicular, and then again next one is parallel. Now if somebody asks me that whether GI is possible in this kind of structure, let's understand. With respect to first and second ring, no. Because these are again what? The groups are in different plane, and different plane groups have same L1 and L2. Okay, but if you talk about with respect to first and third, yes, it is possible because both of these are in the same plane. So here distance of L1 and L2 is going to be different. Basically, when Me is here, this bond can also rotate and this bond can also rotate. Both of these chains are going to be in the same plane all the time. So now these two right now is L1. If it will be shifted over here and go down, it will become L2, and L1 and L2 is going to be different because they are in the same plane, and hence it will show GI. So first and third, with respect to first and third ring, yes, GI is possible. With respect to first or second or third, GI is not possible. So just understand this. If the groups are in the same plane, they can show GI. If groups are in the different plane, they cannot show GI. So this is the main key of the of these kind of structures. Okay, so this is about diphenyls. Now we'll see few questions very quickly, and then we'll move to carbon double bond nitrogen cases. Now try out in these questions whether GI is possible or not, and then we will discuss the answers quickly. Okay, so now look at the answers. I hope you would have done it. So we talk about the first spirene. This is an odd spirene. Odd spirene. So basically this is, if let's assume this is parallel to the board, first spirene, then this is second spirene is going to be perpendicular and third is going to be parallel to the board. So basically first and third spirene are going to be in the same plane, and the groups attached are going to be in the same plane. So groups attached here are going to be perpendicular to the board, and this is also going to be perpendicular to the board. Okay, if you don't remember, you can quickly go through the video, older video, and come back to it. And that's how we understand that this can show GI. You don't have to even go that much, just understand this is an odd spirene, two different groups are attached, it can show GI. Okay, now look here, this is also an odd spirene. Here you have CH3 and hydrogen attached, but here you have CH3 and CH3 attached. So two same groups are attached over here, and hence it, though it could show GI if there would be two different groups here, it cannot, because now two same groups are attached over here, so no GI. This is even alkylidene. Basically these HCH3 and this HCH3 is going to be in different plane, and hence no GI. This is even alkylidene. Okay, come to the next one. These two are going to be in two different planes, hence these groups are going to be in two different planes. Even spirenes, no GI. Look at this. This with respect to first and second and third, no GI. With respect to first and third chain, GI is possible. Now let's see whether we have same groups or different groups. So we have two different groups over here and two same groups are over here. So basically one pair is still different, it can show GI. So GI is possible. GI is possible. Come to the next one. Here again it is an odd multiple phenyl structure where with respect to first and third benzene you will have GI. Two different groups are attached. Yes, two different groups are attached and hence GI is possible. Come to this one. These two benzene chains will be in the different plane, hence the groups would be in different plane and hence no GI. So I hope you would have got it. If you have not got it, you have to actually go through the older video to get much more clarity, because this is just the last part of the whole older video what we have covered. Now we will talk about geometrical isomerism in carbon double bond nitrogen structure. Now let's understand GI in C double bond N system. First of all, we will understand how this carbon double bond nitrogen system forms, and then we will see GI in it. So basically, if you have taken any carbonyl compound is the one which has carbon double bond oxygen. So basically all aldehydes and ketones come under this. Okay, so you have taken a carbonyl compound and you have reacted it with ammonia derivative. NH3 is ammonia. Now, instead of one hydrogen of ammonia, if you have placed any other group, X, Y, Z, whatever group it is, chlorine, bromine, OH, benzene, anything, any group it can be. So any group which has been replaced by one hydrogen, then the molecule which will form is called as ammonia derivative. So this is your ammonia derivative. Z is to just represent that any group it can be. Now, in the mild acidic medium, the reaction happens between ammonia derivative and carbonyl compound. And how that reaction takes place? Two hydrogens from this and oxygen from this goes together and loss of water molecule takes place. So, minus H2O. And then nitrogen gets directly connected to the carbon with a double bond. Now, carbon has two groups A and B over it, and nitrogen has one lone pair and other group which is Z over here. Even the lone pair is considered as another group. Okay, so now this kind of setup has been formed. If this A and B is different, then GI is quite possible. If this A and B is same, then GI won't be possible. So GI is with respect to the lone pair and Z on the nitrogen. So now we will see GI is possible only if A and B are different. If A and B are not different, then GI will not take place. That's a straight simple rule. Now let's see some examples. I have taken a formaldehyde over here and reacted it with H2NZ. Z again I have not mentioned what group it is. It really doesn't matter because it won't affect the reaction. So oxygen from here and hydrogen from here will go together and will form a structure like this. Now, as I mentioned, if A and B are not different, then the reaction, then the GI will not happen. So here, A and B both are hydrogens, hence no GI. Okay. How do we judge what is GI? We don't use the cis and trans term over here. We use syn and anti to represent the geometrical isomers, and that I will explain you with respect to the molecule where you have two different groups. So you will understand why this cannot show GI. Okay. Now here another group I have taken, another compound I have taken, and that is acetaldehyde, or you can say ethanol. And here you have hydrogen, CH3 double bond O, again oxygen and hydrogen will go together, loss of water molecule will happen and these groups will attach, right? So now you have a lone pair over here, a Z over here and two different groups here. So it can show GI. Now let's understand how it can show GI. Basically, GI here is with respect to the lone pair. Okay, if lone pair is in opposite position to hydrogen, aldehydic hydrogen, if the lone pair of nitrogen is on the opposite side or in the diagonal position to the aldehydic hydrogen, then the molecule is called syn. Or you can say lone pair is in the same plane with any R group, then it is called syn. If it is in the same plane, if the lone pair is in the same plane with hydrogen, or the lone pair is opposite to the R group, then it is called as anti. This is specifically for the cases where aldehydes are going to react with the ammonia derivatives. So you can remember it either way. Lone pair is opposite to the aldehydic hydrogen, and the lone pair is in same plane as the aldehydic hydrogen. So I have just mentioned the same thing over here. When lone pair is in the same side as aldehydic hydrogen, then anti, otherwise syn. Now I have taken an example where instead of taking an aldehyde, I have taken a ketone. Now in ketone there is no hydrogen, so we cannot take hydrogen as a reference to figure out syn and anti. So here, if you do the reaction again, water will go out, loss of water will take place, and this is how the molecule will look like. So this has two different groups over here, two here, it can show GI, but when it will show GI, we cannot specifically mention or write what is syn and what is anti. I'll tell you why. Here at least we had a reference point of hydrogen. Here both are R groups, and lone pair isn't the same plane with one R group, but is in the opposite plane with the another R group. So there is no specific definition how to define syn and anti in case of ketone based compounds. So we just leave it, we don't do it. Different books have different ways to do it, so we don't have to ever mention whether the molecule is syn or anti. The only question what they ask you from this part is whether this compound can show GI or not. They never ask you to specify this is syn or this is anti. So because there are no specific scientific rules have been made to figure out what is syn and what is anti in such cases, so we just skip it. We do not go deeper into it. We do not understand which one will be called as anti, which one will be called as syn, but it will be showing GI. That's all we need to know. Okay, now I'll show you some reactions where I'll show you this basic reaction in multiple different manners. Basically I'll be writing different type of Z, what can be there in an ammonia derivative and what kind of compounds it can give you, so that whenever you will see a reaction, you'll be able to relate it better, and then you'll be able to write what is GI. Right now here you have written a generic form, but what all different compounds can happen, what all different compounds are possible and can do the reaction, that we will understand in the next set of reactions. So now these are some examples where I will tell you what is NH2Z and how the reaction takes place. So here I have not taken any specific aldehyde or ketone. Instead I have just shown the carbonyl group. Rest of the other groups which are present over here will be placed accordingly over here. So I have not just taken any example of any carbonyl compound. Only thing what I have done is I have just kept changing the ammonia derivative. So first ammonia derivative what we have is hydroxylamine. Instead of hydrogen here we have an OH over here. Okay. Now when the reaction will take place in the mild acidic medium, oxygen from here and hydrogen from here will go together, and this is how the compound will be formed. This compound is called as hydroxylamine. Hydroxyl is because of OH, and amine because it's a normal amine group. And this molecule which forms after the reaction is called as oxime group. Mind it, this is a very important group, this oxime also and this hydroxylamine also. Both of these are quite important, and you will be encountering these names again and again in aldehyde ketones chapters, and then amines chapters, carboxylic acid chapter. There you will find the questions on these very often. Okay, so you need to remember them. Next reaction is C double bond O, again a carbonyl group, and hydrazine. Hydrazine is nothing else but NH2. NH2 is called as hydrazine. So basically one hydrogen has been replaced by NH2. That's all. Now when the reaction will take place, two hydrogens from here, oxygen from here can go together and it will form C double bond N, NH2. This is called as hydrazine and this is called as hydrazone. Okay. Next is the same thing. Only difference is you have NH2, instead of NH2, NH2, you have NH benzene, and hence the group will be called as phenylhydrazine. And when the reaction will take place, hydrogens from here will go along with the oxygen and will form phenylhydrazone. Next is again a carbonyl compound and 2,4 dinitrophenylhydrazine. This is a very, very important compound. This is used for testing the aldehyde and ketones also. Basically test for aldehyde and ketone can be done through this. Now how it is called as 2,4 dinitrophenylhydrazine, just understand. Hydrazine is nothing else but nitrogen, single bond nitrogen, and any group present over here on nitrogens. Basically this is your hydrazine group. So this is NH2, this is NH, and then benzene is present. So this is almost like phenylhydrazine. Here benzene is present, but not only pure benzene, but it has nitro groups attached. And where all the nitro groups are attached, so this is, if I consider this as the first position where NH is attached, NO2 is attached on the second position, and then fourth position Correct. That is the reason why this is called as 2,4 dinitrophenyl. Earlier was phenylhydrazine. Now this is 2,4 dinitrophenylhydrazine. In short, it is also called as 2,4 DNP. You will find this name also very often when you will talk about aldehydes and ketones. So when you do this reaction again, hydrogen from here, oxygen from here will go together. Loss of water will happen and the molecule will just connect as it is. This will be called as 2,4 dinitrophenyl. Instead of hydrazine, we'll be just calling it hydrazone. That's all. And this is used for testing aldehydes and ketones, and it gives you a specific precipitate. So precipitate color may vary from aldehyde to ketone, and the kind of aldehyde you have taken, kind of ketone you have taken. So generally it varies from the range of red to yellow to orange and so on. So I have just written a yellow precipitate. So this is just to distinguish and identify the presence of aldehyde or ketone in the system. Now next comes to the last ammonia derivative. This is again carbonyl group present over here, and you have NH2 NHCONH2. So basically this is this NH2, and then instead of hydrogen you have NH double bond O and NH2 group present over here. So here the question is, I have two NH2s, one is here and one it is ending with. So when loss of water has to happen, ideally it can go, hydrogen can go from any of the two systems, right? But it will not go from any of the two nitrogens, it will go from this NH2 only. Why? Because this nitrogen cannot lose its hydrogen easily, because its lone pair is already involved in making in the resonance with CO, and hence the bond strength is much stronger. It is not a sp3 hybridized, but it is sp2 and so on. So that's why this NH2 will not involve in the reaction. Instead only this NH2 will involve and will lose its hydrogen, will give away hydrogen and oxygen. Loss of water molecule will take place and the molecule will just connect as it is. This is your carbide group. This is called as semicarbazide. This group is called as semicarbazide, and the resultant group will be called as semicarbazone. Out of all these groups, what all are important, I'll tell you, which you will be encountering again and again. Oxime is very, very important. 2,4 DNP is very important. Hydrazone. These three will be the ones which you will be talking about, and you will be seeing them in reaction again and again. Semicarbazone you won't see much, semicarbazide you won't see much, phenylhydrazine you won't see much, but even if you don't know the names, but at least you should know how the functionality works and how the reaction takes place. Now depending upon what all groups are present on the carbonyl group, it will depend whether the molecule can show resonance or not. It will not depend on the nitrogen, because nitrogen has a lone pair and the different group. What is present along with the carbon, that will decide whether the GI in a particular molecule can take place or cannot take place. Okay, now I'll give you two questions. Try solving them on your own, and then we will discuss the answers. Now try out these two questions. These are based on whatever reactions we have learned just now and the concept what we have learned for GI on carbon double bond nitrogen. So try out these and then I'll discuss the answers. Read the question very, very carefully.